Hello and welcome everyone. Let's continue the Sean Prazard list by solving the maximum depth of binary tree. And this problem is really similar to a question that we solved a while back, minimum depth of binary tree. I was actually confused and I thought that Leetcode had repeated the question when I saw this problem, but then I saw that, oh, this is maximum and that was minimum. So basically for this tree we are given the roots of a binary tree and we want to return its maximum depth. This means that the longest path from the root node to its leaf node. So leaf nodes are basically nodes that do not have children. So these are the leaf nodes. So the longest path from the root node to any of the leaf node. So the leaf node, this is a path of 2, this is a path of 3, this is also a path of 3, and the maximum is basically 3. Now, for a more detailed explanation, I would have to refer you to the video that we made on minimum depth of binary tree. It's going to be linked somewhere in the cards. Do check that out. That goes in depth, and if you do watch that video, I am very sure that you would not need to watch this video anymore, because it basically details everything you need to solve this problem in that video, including the code, right? Everything is similar, but for the sake of formalities and those who have watched that video but are here to just watch this and see how it goes, let's just do a basic rundown. But again, for a more detailed walkthrough, I am going to ask that you please watch that video. All right, so we are given the maximum depth of binary tree and we want to find the longest path. We said in that last video that when we are traversing or trying to manipulate data in a binary tree, we either run a depth first search or a breadth first search. So depth first search means that we're running a level of that traversal where we are traversing the elements of a binary tree according to its level. So this is level 1, this is level 2, and this is level 3. Basically, we are traversing it according to its level. And there are problems where this technique might come in handy, but for this particular problem we are looking for the depth, right? And the cookie is in the jar, the name is in the problem. We want to find the depth of this binary tree, so it is much more efficient that we try to solve this problem using the depth first search, whereby we are searching for each depth, right? We search for each depth, and then we kind of like pick the maximum depth that the tree has. So let's give ourselves some room. So I've given us some room and I have taken time out to write out the problem. So we have this binary tree and we want to find the maximum depth. So we're going to be running a depth first search. How a depth first search works is the depth first search traverses the root down to its leaf node, and when we get to the point where we have nothing else to traverse anymore, it kind of like goes back and traverses another route and that another path, right, that we have not yet visited, and on and on and on until we traverse all of the path. We are going depth first. So we are going that when we pick a path, we are walking along that path and just checking for the elements or whatever problem we want to solve using that path. But for this problem we want to check the longest path. So what we'll do is that for each path that we are traversing, right, we will take note of the number of nodes that we are encountering along that path, and then we can just at the end of it return the maximum. So when we traverse this path, we would see that this is going to give us one node. This is going to give us one node, and this root in itself is one node, right? This is going to be one node, 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 and again this is going to be one node, since they're all connected to the root. And once we add them up, 1 plus 1 will give us 2 here. 1 plus 1 plus 1 here is going to give us 3. 1 plus 1 plus 1 is going to give us 3. So basically we're going to traverse each node, take down the calculate how many nodes we have visited in that particular trail down that path, and then we can just return the maximum. Okay, so let's jump right into the code now. Oh, and by the way, the time complexity for this is going to be O of h. Basically we can traverse as much as the total height of the tree. In fact, we are going to, because we're looking for the maximum depth. To find the maximum depth, we definitely have to trail the highest or the longest height in our tree, which is this. So we're essentially traversing the entire input given. That is linear, O of n or O of h. And for the space complexity, we will be solving this recursively, because we're kind of like repeating ourselves. It's a repetitive code. When we are traversing down this path, we're basically just moving down a certain path, and so we'll be using the call stack. They were using recursion uses call stack under the hood. By the way, even if we had not done this recursively and we had done this following the iterative method, since we are using the depth first search method, we'll still have to use a stack data structure, just like how the breadth first search uses the queue data structure, and we are still using an extra space, which will still be an O of n space complexity. But since recursion uses call stack under the hood, there is no need for us to have to repeat ourselves and declare a stack data structure. We can just take advantage of recursion, and that is what we are going to be doing in this code. All right, so I have written the code. Like I said, this is basically the exact same code that we wrote for solving minimum depth of binary tree problem. The only difference is we are returning the maximum of the left subtree and the right subtree and adding it to 1. With the minimum depth problem, we're returning the minimum subtree. So what we are basically saying is that we are defining a base case, right? If the root is none, then return 0, because there is nothing to work with. Then if the root is a leaf root, and how do we know that it's a leaf root? It's if it does not have a left child and a right child. So if the left child is none and the right child is none, we want to return 1. Then we want to run a traversal on the right side of the tree. So basically the right depth, as we can see here, is calling the function again. So we're running a traversal on the right end of the tree, and we're running a traversal on the left side of the tree, because basically our tree is a binary tree. It has the left child and the right child, and to traverse both, we are running a traversal on both, and we are returning the maximum from the traversal of each side, the left side and the right side. And again, recall that the left side is the root is calling the function on the root dot left, and the right side is calling the function on the root dot right. And if I try to submit this, we're going to see that it works. Again, the time complexity and the space complexity is linear. Also, let's look at the JavaScript code quickly, and it's going to be the same thing with the Python code, but with a different syntax, right? So of course we're checking for our base case. If the root is null, we want to return 0. We're also checking if it is a leaf node. And how do we know that our root is a leaf node? If it doesn't have the left and the right child. So we're returning 1. And then want to check if our root is a leaf node. If it is a leaf node, we want to return 1. And how do we know that it's a leaf node? It's a leaf node if it does not have a left and a right child, basically if they are null. And we also want to confirm that if our left child is null, then want to run a traversal down our right node, and same for our left node. We want to run a traversal both on the left child and on the right child, and at the end of this traversal we want to return the maximum number that we have gotten from traversing both sides. If we submit this code, this should run, and the time complexity is the same. Thank you so much for watching this video. I hope you found it helpful. Again, for more detailed walkthrough, please check out the minimum depth problem. Is going to be linked in the card. And yeah, I'll see you in the next video. Do comment whatever you think I might improve on, suggestions, or any thoughts that you might have. I'll be glad to hear from you. Thank you for watching.